So the warm-up question, you've got 3 questions up here, and they are all asking you about this electric field line diagram. We talked about field lines in class 2 days ago in the first set of notes for this unit. So hopefully you remember those things, because I don't think they were very difficult concepts. It's just going to require you to memorize a couple of things. And so this question is asking you which of these has the strongest charge, and they are numbered Q1 and Q2 so that you can identify which one is which is positive and which is negative. And so looking at this, again, we went over how to tell if something had the strongest charge or how much charge it had, relatively speaking. So looking at this diagram, which one has a stronger charge, Q1 or Q2?
1.
Yeah, 1. And again, what we're looking at specifically are the number of field lines or the field line density. There are more field lines surrounding Q1 or coming, or rather going into it. And so it's going to have a stronger charge than Q2. I know it's not in there yet, so right now we're just going to go over it. You can write it on paper. Number 2, which one of these is positive? If either, maybe none of them. I don't know. Let's look. Okay, anybody know which one's positive? Q1, Q2, or neither? Yes, sir. Q2. Okay, again, we can tell the charge by looking at the direction of the arrowheads on those field lines. And the arrows are always drawn in the direction that a positive charge would move. And so if I'm looking to figure out which one of these is positive, I know that like charges repel, meaning it would push it away from it. The one that shows arrows pushing away from it is Q2. And that's how you can tell if you have a positive charge, as those arrowheads will all point away from that point charge. So Q2 is positively charged, and of course that does mean Q1 is negatively charged. These are opposite charges. We can see attraction between them, but you can tell that you have a negative charge for the same reason. Looking at those arrowheads, in the case of a negative charge, they're going to point toward it. Okay, so those are some of the rules that we talked about in our notes a couple days ago when we were discussing field lines. So hopefully you were able to remember that and apply it to today's warm-up question. We are going to take notes today on transfer of charge, and we're going to, you're going to start an assignment, 1002.3, Electrostatics problem set, but it's not due until Monday because you actually won't be able to finish the whole thing until we've gone over the notes on Monday. So you'll be able to do part of it, but not the math, because we're going to do the math on Monday. So let's go ahead and get into today's notes. And again, you should have a notebook out so you can jot some of these things down. So transfer of charge. You guys did this in the lab yesterday. You were causing charges to be transferred between tape. And so we're going to talk about different ways of transferring charge today. There are 3 different methods by which you can cause transfer of charge, and those are friction, conduction, and induction. And we're going to go over each of them in just a moment. But you can see here this little girl going down a slide, and maybe you've experienced this, but look at her hair at the end. There's very obviously transfer of charge there. She's a buildup of either positive or negative charges. We can tell which one by looking at that triboelectric series that you saw yesterday. But her hair all has the same charge, whatever that charge is, and it's causing it to each strand repel the others, which makes it stand on end, and it looks kind of funny and kind of cute because, it's a little kid. I don't know if I would think it was cute if it was my hair, but it looks good on a 2-year-old. So anyway, you have here an example of charging by friction. Whenever you have one object that rubs over the surface of the other, you can have one of them strip electrons from the other, and then you have one of them that is negatively charged because it has all these extra electrons, and the other will be positively charged because it lost them. Okay, and so we're going to go into more details on each of these, friction, conduction, and induction. But for now, those are the 3 different types, and you can save some space underneath them to copy down what's happening. Okay, so here is charging by friction. Okay, again, electrons are capable of transferring from one object to another. This can happen by friction. That was the first method, which is going to occur when you rub 2 neutral materials together so that one of them can strip electrons from the other. It's typically done with 2 insulators. You guys did this yesterday in your lab. I had you rub a balloon on your hair, same thing. When you rubbed that on your head, you were causing electrons to move from one to the other. And you can see here in this animation the same thing. This is a rag, some kind of cloth, and a PVC pipe, and they're showing the charges in each. And you can look that as they rub the PVC pipe on this cloth, it strips away the electrons, leaving the cloth with a positive charge because it lost a bunch of electrons, and leaving the PVC pipe with a negative charge. And that's the same same thing that's happening whenever you rub the balloon on your hair. It's the same thing that happened with the little girl going down the slide. You have one thing that's stripping electrons from the other. This is actually what was happening to the little girl as well. Plastics typically do become negatively charged, especially PVC. But anyway, you can see here that animation where you can see the charges. Note, and I have this at the top, and somebody's probably going to put it on their quiz and on their test. Please don't let it be you. It's a common misconception, okay, but you cannot transfer protons. If I ask you, hey, here's two things, and this one became positive and this one became negative, and I say, how did this become positive? Don't tell me it has extra protons, because it doesn't. Okay, it's not the protons that are moving, it is the electrons. So for something to become positively charged, it's not gaining protons. Instead, it is losing electrons. Okay, we talked about this in our notes the other day as well, but I'm telling you somebody's going to miss it, because somebody misses it every year. So again, don't let it be you. Write that down in your notes. But you cannot transfer those protons. Those protons are in the nucleus of the atom. We're not breaking nuclei apart. That would be a nuclear reaction. We are simply stripping electrons off. There's no reaction happening here. It's just transfer of those charges. Here is a video of Bill Nye going over an example of transfer of charge. Just give me 2 seconds, because I just realized I need to get the sound turned on. This demonstration that he does, and then we'll talk about it a little bit afterward.
So, hi. Rub a balloon on your hair and bring it near another balloon hanging by a string. There's an invisible field pushing the two balloons apart. When you rub the balloon on your hair, you're transferring electrons from your hair onto the surface of the balloon. Now, the balloon's made of rubber. Electrons don't flow through it the way they do through a metal wire. Instead, they stay on the surface of the rubber. We use the word static electricity, which means electricity that stays. Now, different materials have different properties. Here's a stiff rubber rod and a piece of fur. It's like rubbing a rubber balloon on my hair. It also will push the balloon away. But watch what happens when I use the same piece of fur and this glass rod. It pulls the balloon toward it. So in the first case, we say they have like charges, like static charges, so they repel. In this case, they have opposite static charges, so they attract.
Okay, that is what you saw or hopefully what you saw in the little lab that we did yesterday, is you saw pieces of tape that were attracting, you saw pieces of tape that were repelling, you looked at their interactions with the balloon as well, but you can see the result of that electric field and the result of the charge buildup that you've created when you charge something by friction. So all of these are examples of charging by friction. He charged the balloon by friction when he rubbed it on his hair. He charged the rubber rod by friction whenever he rubbed it with that fur, and same thing with the glass rod. Okay, so again, you can use that to strip electrons, and you can tell which material will gain them and which will lose them by looking at something like this. And this was also in your lab, but it's called a triboelectric series. And so if you're trying to determine which object becomes negative and which object becomes positive, you don't have to memorize it. You have to be able to read a chart. Okay, and this chart shows the tendency of these objects to gain electrons versus losing them. And so it ranks them, because if you rub any two of these objects together, whichever one is higher up on that list, and the way this one is drawn, sometimes they're drawn in reverse, so pay attention, but whichever one's higher up on my list on my screen is going to become positively charged, which means it is going to lose electrons. And if you rub it against something lower down on the list, that object's going to take them. Okay, so if I rubbed, for example, nylon, like pantyhose, okay, on a balloon, you're going to have the nylon losing electrons becoming positive, the balloon will gain them becoming negative. But I could also rub like nylon and wool. Even though they're both toward the top of the chart, it doesn't matter. You look at which one is higher. That one will become positive, the one below it will become negative. Okay, so you can tell by looking at this which objects are going to gain electrons, which objects are going to lose electrons. And again, I can tell which is which because it says these are positively charged up here. So again, you might want to add the words if you're trying to copy down something like this in your notes. Where that positive charge is, you might want to add the words loses electrons. Where that negative charge is, you might want to add the words gains electrons, because again, that's how we're obtaining the charge, is by the transfer of those electrons. So again, pick any two objects. Here's your hair and a balloon. That's one that you did yesterday. And you saw this yesterday when you rubbed a balloon on your hair gained a positive charge. The balloon gained a negative charge. And the reason for that is that electrons were transferred from your hair to the balloon. Your hair was neutral, but once all those electrons are stripped, now you have positive charges in your hair without any negatives to neutralize them. And so now with all these positively charged strands of hair, they don't want to be near each other. Like charges repel, your hair stands on end. Okay, and it makes your hair stick up. The balloon has this negative charge now. If you bring it near your hair, opposites attract. Your hair will stick to the balloon. Yes, sir?
Why when it's humid out, your hair gets like frizzy because it's taking...
So humidity actually usually causes those charges to be able to dissipate, like off of the tape that we used yesterday. I said if it's humid in here, then it'll actually lose those excess charges, or it'll start to exchange them with the humidity in the air. So it's a little bit different. You typically have more static in your hair when it's really dry. I don't know if y'all have been, it's not really dry here, but if you've been somewhere really dry, you'll get more staticky hair. If you've been to like Arizona or Nevada or something like that, and it's really dry out, you're going to have typically more static in your hair. Yes, sir. Okay. Here is the other example I showed you earlier. I don't know what this rag is made out of. I went with silk. Maybe it's wool. I don't know. Maybe it's cotton. Either way, all of those materials are above PVC, which is polyvinyl chloride plastic. That's your PV and C. But this is one of the most negative materials on the list. It is the most negative material on this list, but it does, again, tend to pick up those electrons. So it tends to gain a negative charge. So if you rub PVC on something, you're probably going to get charges. And that's a similar type of plastic probably to what that slide was made out of that girl slid down on our first slide of the notes.
Is there a maximum amount of electrons one thing can have? Is it like you just have to just rub everything?
No, not specifically, but I mean they do repel each other, so at some point it's going to become difficult to continue building up that charge without them repelling each other. Yes, sir?
Is lightning just like a lot of electrons?
Sorry?
Lightning?
Lightning? Oh, yes, that is also a buildup of charge, yes. You can see the discharge with lightning, it's visible.
Yeah.
All right, so the first way to transfer charge was friction. This is the second way. It is called conduction. Okay, conduction occurs when you touch a charged object and a neutral one, or just two objects that have different charges, so that the charges can flow from one to another to reach a balance. When we did charging by friction, you see that more often with things that are insulators, although you could charge up something that is metallic. But with conduction, you're going to have one of them at least that's a conductor so that the charges can flow more easily. So you'll see it with metals and stuff more frequently. The objects you'll be dealing with, at least one of them will be a conductor. But you can see here this boy is touching a Van de Graaff generator. And this Van de Graaff generator does have a buildup of charge on the surface of it, that metal sphere that he's touching. And that charge transfers to him. And so it makes his hair stand on end, which you can see in the image whenever it's turned on. His hair stands up. But again, those charges will transfer from one to the other until they have the same charge. So again, this is kind of what's happening with the Van de Graaff. You have this buildup of charge, and then when you touch it, those charges go into you, including into your hair. And so you can see it in your hair, but you can actually feel it. Like even with your arms, you can feel your arm hair stand up too. with the Van de Graaff, because it's actually generating more and more charges. It's not just however many are there, it keeps making more. And so you can feel that whenever it transfers into you. But again, conduction is going to happen when you touch a charged object to an object with a different charge or to an object that is neutral, and they're going to flow until they reach an equilibrium. So again, I mentioned the words conductor and insulator. We should probably make sure we add definitions for those as well. A conductor is a material that allows the flow of electrons from atom to atom. So you'll have these electrons kind of flowing freely throughout that material. And I believe you also saw an animation showing something similar in the SIMS activity that we started with, looking at the flow of electrons in a conductor. An insulator, on the other hand, those electrons are able to kind of move within the orbital cloud of their respective atoms, but they're not flowing freely like to the other side of the object. They can shift, and you can have polarization, which is what this is showing. When you bring this negative rod nearby, all the negatives move as far away from it as they can, but they're each still attached to their atoms. So they're not flowing freely through the material, but they are able to kind of move a little bit. Whereas these electrons completely detach from the atom, and they can all build up in one region because it's a conductor. They can flow. Conductors allow conductivity or flow of charge. Insulators do not. So if you were to touch a charged object to a conductor, those charges would spread out evenly. If you were to touch a charged object to an insulator, they're going to stay in the kind of localized region where you place them because they're not able to flow in the same way. Okay, so this is the type of question that you might see on a test or a quiz, but this is showing charging by conduction. We have this neutral sphere. It says the charge here, Q, is 0. And this rod that has extra electrons, so you can count them because I made it easy to count. There are a total of 4 protons here and 8 electrons. So its charge is -4, okay, or -4e, -4 electrons. And so we have these two objects that are, I'm going to touch them to each other, and after they touch, you'll notice that my rod now has only a charge of -2, and so does the sphere. Again, whenever you have charging by conduction, the charges will flow until they reach a balance. So you'll get equilibrium. They'll have the same charge at the end. Because again, those electrons don't want to be near each other. They will flow wherever they can to spread out as far as possible. Okay, and so you'll see that here as well. -2, -2, we have the same charge at the end. Okay, so what about this one? If I were to touch a rod that has a charge of -4, with a sphere that has a charge of +6. Same idea. Those negative charges will spread out to the greatest extent possible. Okay, if you want to figure out what they're going to do, and yes, you could do kind of just guess and check if you want, but you can do this. If you want to solve a problem like this, and it's not necessarily immediately obvious, then you just start by finding the total electric charge of the system. -4, +6, my total net charge of the whole thing is +2. -4 plus 6 is +2. Okay, and so if I were to divide that charge evenly, which is what's supposed to happen, divide it equally, then both of them are going to be a charge of +1 at the end. Okay, and so you'll just get your total charge, divide it by 2 if there are 2 objects. Each charge will have a +1 charge at the end, which means in order for that to happen, how does this occur? Again, we're going to have to move these electrons. Again, we're not moving the protons, we're going to move the electrons. So this one that has a -4 charge is going to move quite a few electrons, okay, over. And so you're going to end up at the end with the same charge on both, but this will have to have lose 5 electrons, okay, for this to get a charge of +1, which means this one gains 5 electrons, and that results in both of them having a charge of +1. And again, we call this electrostatic equilibrium, and that is what you have whenever you have charging by conduction. Okay, at the end of charging by conduction, the objects will have the same charge as each other. Total number of protons and electrons remains the same. I still have the same total number of each. It's just they have moved, at least the electrons have, from one object to the other. Questions about charging by conduction? Again, might be a good thing to write down. I know that we've had a question like this in the past. So that equation that I gave you a second ago would be a good thing to have to look at as you are making sure that you understand how to do all of these. All right, so this is a Van de Graaff generator again. Van de Graaff generators use friction between a rotating belt and special brushes to transfer electrons to a metal sphere. This is what the boy was touching earlier. So I'm going to show you these this stack of aluminum pie pans that are sitting on top of this Van de Graaff generator. I want you to watch what happens. It's in slow motion. It happens very quickly if we do it in the real world. So it looks like they're defying gravity, basically, okay? Which is just because, again, this Van de Graaff is generating all of these charges, and they're transferring to the pans because both of these objects are metallic. So we have charging by conduction, but now these pie pans don't want to be near each other because now they all have the same charge, and so you're going to have them fly off one after the other. Sorry, I'm trying to start it again. They're going to fly off one after the other afterward, okay, because they all have the same charge. And so you can see it happen as the charge builds up and it transfers from one to the other by conduction. They're going to just fly off one at a time. So this is kind of what you have here. When it's off, it's not generating those charges, but when you turn it on, you have this generation of, charge, negative charge here, and they're going to transfer to the pie pans as well. So these are the excess electrons. They still have the same protons that they started with, but now they have extra electrons, and when they're all negative, they don't want to be near each other. If they can leave, they will, and they are able to just fly off like that. And so you can see them look like they just jump off of the stack. Okay, so that was the first two ways of charging. Friction and conduction. This is the third. This is called electrostatic induction. Okay, so this is the process in which redistribution of charge takes place within a body when an electrically charged body is brought near it without touching. And this was one of the simulations you guys did the other day. So you can see this charged body brought near the insulator. You can see what I was talking about earlier. All those electrons are still trapped in their orbits, but they can polarize or kind of shift in one way. Whereas your conductors, you have all of your electrons able to move freely. And so what's happening when you have electrostatic induction? Well, obviously you have polarization. That's the first step, and you can see that in both of these examples. Because you end up with your positive charges more generally concentrated to one side and your negatives more generally concentrated to the other on average. It is obviously much more noticeable in a conductor, but it happens in both. Okay, so induction causes objects to become polarized. Polarization is the process of separating opposite charges in an object, leaving one side with a positive charge and the other with the negative charge. One side has more electrons on average than the other. Or in the case of the insulator, you just have the electrons just shifted closer to one side than the other. But you start with polarization. Okay, this actually takes a couple of steps to charge something by induction. So step one is to bring a charged object like this rod or like this balloon near another object causing polarization. Okay, and so we get polarization in those other objects. Okay, what is the charge of the conductor and insulator afterward if we're looking at the insulator here? Well, there has been no transfer of charge. Okay, so both of them still have the same charge. So the insulator in the wall is still neutral. Over here, it's still neutral. In fact, so is the conductor, still neutral. Okay, and the rod still has the same charge it had. Nothing has moved because nothing has touched. Same thing with the balloon, still has the same charge that it has. Okay, so you have no transfer yet. Okay, so if we look here, the charges in a wooden rod and a steel nail are shown below. Notice that each has an equal number of protons and electrons, meaning that both are neutral. Okay, if you were to put a Van de Graaff generator with a negative charge near them, the charges in the wooden rod and steel nail that are near the negative sphere are shown. Okay, so my nail, all of my negative charges move to the tip of the nail, Whereas my rod, which is made out of wood, they can't move to the end like that because this is an insulator, but they can cause polarization where they're arranged like this with the plus side closer to this, and each of those respective atoms has their negative charges kind of shifted the other way. Their orbitals shift. Okay, but that's why your distribution of charge looks different, because one of these is a conductor and one of these is an insulator. Okay, so this polarization is temporary. If the charged body is removed, the electrons will return to their normal positions. So you haven't actually caused any transfer yet. If you move this negative rod away, it just goes back to how it was. Okay, so you bring it near, you get this polarization, but then when you move it away, it goes back unless you add another step. Okay, so this polarization is temporary. Okay, so the next step is when the separation of charge is induced in two touching conductors, they can be separated, which is what you see down here. So you bring the charged rod close, you cause the polarization of these two rods that are touching each other, and then if you physically separate them because you caused polarization, now the rod on the right-hand side over here becomes negatively charged because your electrons are more concentrated here. The rod on this side becomes positively charged because its electrons are shifted over to the other one. So you can actually create charge by bringing a charged object near to maybe two other objects that are touching and then separate those two objects. And because you polarize the charges first, now you have two charged objects. One is negative, one is positive. That is one way that you can charge something by induction. Okay, is by bringing a charged object close. There's no touching involved there. You just bring it nearby, and then the two objects that you had that were touching, that were neutral, you separate them. Okay, and so this is illustrated here. You can look back at this some more if you want. There is actually a link here to this simulation if you want. This is on slide 39. You're welcome to do that on your own. Okay, you can also see an example of charging by induction with an electroscope, which is a tool that we can use to determine whether an object has a charge in the first place. So you can see this electroscope here. It has a disc at the top. Sometimes it's a metal ball at the top, but there is a rod that goes down and attaches to these two leaves that are typically made out of a very thin strip of foil. And so if you have a charged object like this negative rod or this positive one and you bring it nearby, you can see that this electroscope is neutral, but when this comes close, we get that same polarization we saw before. This one forces the electrons down into these leaves. Because these leaves are such thin pieces of foil and they're very lightweight, you can see them move and repel from each other when they have those negative charges. In the same way that you saw your tape do that, it's the same thing. You'll see them physically move apart from each other. Or with this one, it's the same idea, but this is a positive rod, so instead of the negative charges going down, in this case they all go up here, but that leaves the leaves at the bottom positively charged because they've lost most of their electrons. Like charges repel, and you see that in the leaves. Here's an actual electroscope that somebody built that has a metal loop at the top, and you can see the leaves in the jar at the bottom. They charged up the comb simply by brushing their hair. And if you bring it nearby, you can see those leaves move because they have the same charge. Now, you can't tell the charge of an object by looking at an electroscope because you don't know. You'll notice they look exactly, leaves move in both. Okay, you don't know if the object is positive or negative. All you know is that the object has a charge. Okay, so an electroscope will tell you if you have a charged object. It won't tell you if the charge is positive or negative because it looks exactly the same when we look at what's happening, because we can't obviously see the charges moving in real life like we can in that simulation. Okay, so here is another way to charge by induction. So one of them was causing polarization of two objects that were touching and separating them. The other involves another step called grounding. Okay, charge can be added or removed by grounding, which allows objects to reach electrostatic equilibrium. So if you look at my simulation here, starts out as a electroscope that is neutral. Okay, and so I'm going to wait for it to reset. But it starts out neutral, and you can bring this rod close to it and cause those charges to separate as they did before. But then if you touch it, okay, you can actually cause charges to move into or out of your hand, giving the electroscope an overall charge. And you can see the electrons just came in through his hand back into this electroscope to cause grounding. So you can use grounding to neutralize the charge, and that's what I was telling you about in the lab the other day. Whenever I said if you touch the tape too much, then you're going to have to recharge the tape because objects will reach that electrostatic equilibrium whenever you have grounding occur. But you can also touch something whenever you're causing polarization, and you can create the charge in the first place. Okay, so why do the charges flow from the hand into the electroscope? Well, because the electroscope, when it resets, had a positive charge. It was missing electrons, so as soon as you touch it, it steals some of yours, and now you have this equilibrium again. So grounding is the process of removing excess charge on an object through transfer of electrons. When a charged object is grounded, the excess charge is balanced by the transfer of electrons between the charged object and a ground. Okay, anything touching the ground can be a ground. So you're touching the ground, you touch it, you can ground it, because it's basically transferring electrons to and from the common stock of them in the earth. Okay, so there are a lot of them there. But you can neutralize or uncharge something by grounding, or if you have polarized it and touched it, you can actually cause those charges. If you're still holding the charged object nearby, you can actually charge an object in this way too. All right, so in summary, here are our three different charging methods. Friction. If we rub two neutral objects together, we can cause one to steal electrons from the other. Conduction, we can touch a charged object to an object that has a different charge, and electrons can transfer until they reach the same charge. And induction requires bringing a charged object near a neutral one to cause polarization, and then either separating the objects or touching the object, and if grounded, the objects could be oppositely charged afterward. Okay, so there are different ways to do this one, but it starts with polarization. Again, still need to know that you're not transferring protons in any of these. All of these involve the transfer of electrons. Okay, ultimately these interactions boil down to a few general ideas and rules. And again, I just mentioned one of them. Protons are positive, they don't move. Electrons are negative, they do move. Okay, that's that first rule. Okay, opposites attract and like charges repel. Electrons repel one another, so they will spread out until equilibrium is reached. Materials lacking electrons will attract or take electrons until equilibrium is reached. If you give them a source, they're going to take it until they reach equilibrium. Okay, so again, these are kind of the general rules that we just talked about with all of those. All right, guys, for the rest of the class period today, you do have an assignment, 1002.3 electrostatics problem set, but you can't really work on the first 8 problems yet because we haven't done the math yet. So it's actually the second half of the assignment, questions 9 through 18, that you can work on because it's what we covered in today's notes. We will cover the math portion of the material in class on Monday. That will be the first 8 questions of it. You guys do have a quiz next week on Tuesday, and you do have a test next week on, that's not supposed to say Friday, it's supposed to say Thursday. But you have a test next week on Thursday. Okay, so you do have those dates coming up. Go ahead and get to work on your assignment. If you have any questions for me, please let me know.